All right. So today I want to explain something about cylinders, cones, and circles and how they're all related. And since I'm quarantined out of my classroom, I've got my daughter's whiteboard here. See, she's decorated the edges for us. And as far as whiteboard markers go, I'm going to open up her sparkly purple whiteboard marker container here. All right, so we've got a blue marker. Let's see if this one works. And we're going to draw a few shapes. So let's imagine that we have why don't we start out with a circle? So we have a circle. And this circle, remember, will have a radius. But let's also imagine this circle in 3 dimensions, which makes it more of a ball shape, which we would call a sphere. Okay, so we have a 3-dimensional circle that we'd call a sphere. And now let's imagine that we had a cylinder that was exactly the same height. So we have a cylinder that is exactly the same height. Now, I don't know how well I will draw this, but we have a cylinder that is exactly the same height as this sphere, this ball, so that if you put the ball inside the cylinder, it would touch the edges here and would also touch the top and the bottom. So your ball would fit perfectly inside. You could not fit a bigger ball, and the tops and the bottoms filled that up completely. Now let's also imagine one more shape. Let's imagine a cone that had a circle this exact size on the bottom, and then it touches the top of the cylinder. I'll draw it off to the side. So we're going to imagine that this is a circle that fits the exact same bottom as that cylinder, and it goes up the exact same height as the cylinder. Now, what I want us to think about is how the volumes of these shapes might be related. So there might be a connection between all of them, because a sphere is like a 3-dimensional circle, and it has a circle that exact size inside of it, and that would be the same size as the circle on the bottom of this cylinder, and the same size as the circle on the bottom of this cone. So we're wondering, is there a connection between all of these? And the really cool thing is that there is. Imagine that this sphere was full of water, and this cone was full of water. And if we had this cylinder as like an empty tank, I want you to guess, what do you think we'd get if we poured the sphere into the cylinder? Would it fill it all the way up, or only part of the way? If you think about that for a second, you should probably notice, well, it should fill it up part of the way, but not perfectly all the way up. Now then you might think about, well, what fraction of the cylinder would be full? Would it just be some random amount, or would it fit in kind of nicely? We could also ask the same question of, what if we poured in the cone? Would it fill up all the way? No, it doesn't seem like it would. Would it fill up like exactly half? Would it fill up just some weird decimal fraction of it? And here's what's kind of cool. If we poured in the sphere and the cone together, they're actually going to fill this cylinder up perfectly, 100% together, which is kind of amazing. And then the other neat thing is that if you just did part of them, this sphere is going to fill this up exactly 2/3 full, and this is going to fill up the other 1/3, which then also makes the volume of the cone exactly half the volume of the sphere. So let's think about what the formulas would be. So we know the volume of a cylinder. The volume of the cylinder is going to be the base area, which would be pi times the radius squared, and then times the height of the cone. Now, the interesting thing about the height of this, the height of the cylinder, not the height of the cone. The interesting thing about the height of this particular cylinder is that, remember, we said this sphere fits perfectly inside. I'm going to get maybe a red marker. Hopefully this one works. My daughter sometimes doesn't put the caps back on. We'll see. So let's say that that radius is r. Now, the radius up to the top would also be r, and the radius down to the bottom would be r, which would make the total height of this cylinder 2r, 2 times the radius. And that would also be the same height of the cone, and that would also be the height of the sphere, 2 times r. In other words, the diameter of the circle all the way through. So this would be pi r squared, and then times 2r. So we'd get another times r and a times 2. I'm going to put them in this order so that we could group the r's together. And remember, the order of multiplication doesn't actually matter. So let's simplify this formula. R squared times r, well, r squared just means r times r, and then it's another times r. So if we wrote that using exponents, that would be r to the third power, r cubed. And then we would still have the times pi and the times 2. So the volume of this cylinder would be 2 pi r cubed. And then we can actually use this formula to figure out the volume of each of these, because remember I said that this sphere would be 2/3 of the cylinder, and the cone would be the other 1/3 of the cylinder. Now, I wish I had models where I could actually pour water into cylinders that fit out this way, but isolated in my home right now, I do not have that. But I do promise this really does work. I could do a mathematical proof, but the one I know would use calculus. So we're just going to take my word for these ratios, and then that's how we're going to get these formulas. So we've got 2/3 of this would be the volume of the sphere. So that makes the sphere volume 2/3 of this. Well, this is we have 2 pi r cubed, and we want 2/3 of that. So we're going to multiply it by 2/3. And when we multiply fractions, the top numbers can multiply together. So your 2 times 2 can become a 4. So this just becomes 4. So it's 4/3 pi r cubed. If I write that nicer, it looks like this. And another way of thinking of that is 4 times pi times r times r times r, and then divided by 3. That's another way of thinking about it. All right, so that is our sphere volume formula. And then now let's do the same thought process to get our cone volume formula. So the volume formula for a cone is going to be 1/3 of the cylinder. So the cylinder is going to have a volume of pi r squared times the height. So a cylinder volume is pi r squared times the height. And then in this case, the height happens to be 2r, but in general, the cylinder volume is pi r squared times the height. And then we can just think of this as being 1/3 of that. So we can just do 1/3 in front. Or the other way of thinking about it is pi r squared times the height divided by 3. So that is the volume of a cone. So that's the cone volume formula. All right, so that's the trick to figuring out a volume formula for cones and spheres. Sphere has an E at the end. Anyway, I'll do example problems to go along with this in another video.